Okay, so a little bit later than I had planned, but let's go ahead and get into 16.2 and 16.3. Much of these slides are going to set us up with concepts, so we'll go fairly quick. I'll slow down the examples that we will go over here is kind of what to focus on. Those are the way they would appear in the homework. Okay. So line integrals, this is what we've kind of been doing before. They could be one-dimensional, as we're going to see. We can get into two and three-dimensional integrals as well. So it's very similar what we're starting with here as far as line integrals. It's very similar to single integrals, and we integrate over a curve, so it's rather than going from x equals a to x equals b, we're following along on a curve. So that's why they call them line integrals, although maybe we should call them curve integrals. And they get used for various things like fluid flow, forces, electricity, magnetism. So line integrals in the plane. So our first rule is x is equal to x of t. So this is parameterizing our variables x and y into a sort of a third variable, as we started off with very early, and then we let the parameter variable go from a to b. Okay, so we'll take a look at this, and we can think of these as vectors as well, and we make the assumption that C is a smooth curve, meaning that we have that it is continuous and that the derivative is not equal to 0. So those are kind of the rules we start with. And this is what we're doing, is we're basically integrating along a curve. We're taking these little pieces, these change in S1s, and so what we're going to be doing is these sub-arcs become build into something like a Riemann sum, where we were building rectangles and such, or for that matter, rectangular cubes. And so this delta S is a subarc. We're multiplying that by the function value, and so that's giving us something against that we think of similar as a Riemann sum. So we're getting these pieces. This is really just building the theory, saying, hey, we can integrate. When we get to integration part, that's going to be very familiar. So this notation is just building the fact that everything we're doing is built on the theories of Riemann sums that we've used in the past. Okay, so if f is some smooth curve, then we get that the integration is equal to this summation of these sort of Riemann pieces as we let n go to infinity. So the size of each piece becomes smaller and smaller, which means there becomes more pieces. That's that smooth integration. And this occurs only if this limit exists. Of course, if the limit doesn't exist, then why are we talking about it? Okay. And what we get is that the length of the arc, and see, using arc length, sort of for the circle x squared plus y squared, we get this general form for the length of C. Okay, the length of the curve will be this integration from A to B over here. And you're going to see this is important. This will come back. We use this in, there's an example a little bit later on, actually a three-dimensional example using gravity, but the square root of x squared plus y squared, basically. These are, again, derivatives, but that's kind of where we want to think along those lines. So this other one we're going to look at is basically, as long as we have some function, parameterized function, x of t, y of t, we multiply that times this length of the curve. Okay, so this, remember this, the square root part, this part here is going to give us the length of the curve, and this is the function values from A to B. So again, where it gave us before is kind of it gives us sort of an area, right? The length times the width, the height, length times height. So that's going to give us an area. And one of the things we want to make sure is that that the function, the graph, does not cross over itself. And it only goes one time from A to B. Okay, so just kind of some of the parameters that we work with, and just make sure everything's good. So the arc length, again, the ST is the length of C, R of A and RT. The derivative, the absolute value of the derivative gives us this arc length, or gives us this component. When we multiply it by d of t, that gives us that arc length. Okay, so this is going to be a component that is part of our integration, and then we multiply it times the function. Okay, we have the special case where C is going from the point A0, notice Y is 0, to B0, so that's all on the x-axis, and that's just what we've been doing, the one-dimensional or one variable integration in just x. That's what we learned at the very beginning. Now we're just generalizing if these are not the points. So we, y could be different points, so we could actually do a line integral. So we've always been doing line integrals, we just didn't call them that. And again, what this ended up being was the area under the curve, because we're going from some point A0 to B0, and the function would do something, there's this beginning, there's the end. And what that would give us is the height of the function times the length of the curve going from A to B. So it gives us area under the curve. And so if it's not, if we've got a curve going on here, we've got the function value, right, from going from the xy plane gives us some value up here, and what this integration gives us is the surface area of sort of one side. You multiplied by 2 because there's two sides, but it would give us the side, one side of the fence or curtain, however you want to think of this this shape. Okay, so that's, again, these are just getting us what are we getting. We're getting area. So now let's actually go ahead and do these. Let's evaluate 2 x squared y ds, where c is the upper half of the unit circle. So when we go to think of this, we first want to parameterize things, and if we have x and y, one way of doing that, and we're talking about a unit circle here, x squared plus y squared, that gets us thinking of polar coordinates. And so we oftentimes can think of making the parameter that x would be cosine t and y would be sine t. Okay, so that if we parameterize in that way, that works with getting something on the unit circle. Since we want the upper half of the circle, we're going to see the picture here in just a moment. There it is. We're going to go from our angle t, we'll go from 0 to pi. So that kind of gives us our limits. This is our parameterization, and we're doing it over x squared plus y squared. So the formula first gives us, starting here and this. So what we're going to do is a substitution. X will be cosine. So we're going to get oops. Well, we'll get this, but let's walk through this a little bit. That was my intention. Okay, so we make this substitution. We're going to integrate, and again, we know we're integrating from 0 to pi because we're just doing the top of the half circle over there. 2 is still just 2. X squared is going to become cosine squared t. Times y, which is sine t. And then ds, remember that gives us our square root of dx dt squared plus dy dt squared times dt. Okay, so what is dx dt? Dx dt, so we take this derivative, that's going to be cosine, the derivative of x gives us negative sine t, and again that's all squared, so it'll be positive sine squared, plus derivative of y, that's going to be cosine, and that's going to be squared. I'll just go ahead and do that. This will be squared, and then we've got dt. Okay, this becomes sine squared plus cosine squared. That's 1. Square root of 1 is still 1. So that was kind of cool. That's why this parameterization is really very helpful. And so then we have dt 2 cosine squared t sine t from 0 to pi. And when you integrate cosine squared, so that's kind of the chain rule thing, it becomes cosine to the third over 3. So just think it's something cubed, or it was something squared becomes something cubed over 3. The 2's still there. Wait, that's a plus. It's a plus 2. That's a little different. Let me fix that. So we got that one. 2 integrates into 2t plus cosine cubed. And now if you take this derivative, you'll get 3 cosine squared, and the 3's cancel. When you do the chain rule, the derivative of cosine is sine minus sine, right? So we need a negative here, so that, because we don't have a negative. Okay, so that kind of takes care of that. And then we go from 0 to pi. And that's our integration. We'll check it over there, but if we put in the top end, we end up with 2 pi. We put pi in here. Cosine of pi is -1. Cube it, it's still -1. -1 times -1 is +1. So we get a 1/3 there. And then we're going to subtract off what happens when we put in 0. Well, when you put in 0 for t, 2 times 0 is 0. And then when you put in 0 for cosine, you get 1. 1 cubed is still 1. Get this negative, and that negative is going to become a positive. There's a 1/3. It looks like it's going to be 2 pi plus 2/3. And we'll see. I didn't take a real close look at the example, so let's now see if that's actually what we end up with. 2 pi plus 2/3. Wow, that's pretty good. So this is the integration. Again, remember we get this part when we parameterize with the sort of polar coordinates, right? This becomes sine squared plus cosine squared is 1. Square root of 1 is 1. There we go. So there's an example of using this parameterized line curve integration. Okay. So you'll be doing this in the homework. So go ahead and go to the next one. And then we just take, what if we had a curve that sort of had a lot of different pieces, C 1, 2, 3, 4, 5, as long as it's smooth, right? So they're all connected and you could draw through there, it's continuous. So what if we had that, something like this? Well, then we could actually define each piece as an integral. So we could break down a larger integration of a function into several pieces. Or if we have several pieces, we could go back and do it as one big piece, depending upon which one is easier. Now that last one, probably having the pieces is going to be easier because the limits are going to change, right? Okay, so we get something like this. Again, we're doing sort of line integrals, or as we should say, curve integrals. We're following along this curve. We get these Riemann sums. And what it could represent is, if this is a wire, a length of wire, then what we're getting is the mass of the wire. So we're getting the length, the change in S is the arc length of the wire on any part of the curve, and then we're multiplying by this function value, which gives us total mass of the wire. Okay. And again, as we take more and more points, we get closer to basically dividing it into an infinitely number of pieces, and that's when we get the integration. So just like we did on the last one, 2 plus x squared plus y could be the density of the semicircular wire. That's what we would have gotten, the last answer, 2 pi plus 2/3. That would have been the mass of that wire had that been the explanation for it. Okay. We'll look at integrals with respect to x or y. I believe this C is, because I looked at this many times and I can't see the difference. I believe this should be dy. So you have you can either integrate with respect to x or you can integrate with respect to y. And again, this integration really is equal to a Riemann sum. This is where it comes in. So we can also do the same thing. So 5 and 6 could both come down to this. We could parameterize x and y into t, and then that way we're integrating with respect to dt in both cases. But notice we've got sort of this partial derivative with respect to x in the one side, or partial derivative with respect to y on the other. So we're going to look at, I believe, two examples, one where we do a parameterized version, and the other where we really just do one in terms of just one of the variables. Okay. So oftentimes, integrals with respect to y and x occur together. So we could, you could do it separately, or you could join them together if they're going over the same interval. Is kind of the customary way to do that, and it's kind of what we've been doing, I guess. Double integrals in a way. One thing that is helpful is, since we are going along a line segment, we can remember that any function along a line segment from R0 to R1, so going from some beginning point to some point 1 down the road, that it can be parameterized in terms of t by 1 minus t times R0 plus t times R1, and just letting t go from 0 to 1, and then that gives you the parameterization for that function. Okay, so now we're going to look at two examples. We want to evaluate this integral in terms of y and x, and one integrations with respect to x, the others with respect to y, and we're going to go down two different paths. So the first one, we're going along this segment from -5, 3 to 2. So we're going here just along really a straight line segment. So how do we do that? And then we'll come back to B after we do that. Well, first of all, remember our parameterization. If we're going along a line segment, we can parameterize in this sort of way. And so we got the starting point as R0 is -5, -3, and R1 is 0, 2. So if we do that, we get a parameterization where x is equal to, plug in a 5 here, right? So plug in the x coordinate 5, so you get a plus 5. And R1 is 0. This was clear last time. Okay. 5t minus 5. Okay, I'm back on track. So these are vectors, so we get 1 minus t R0 is going to be minus 5, and if you want to, I kind of like to go with this, the minus 5i minus 3j. That's kind of a, I guess I don't really need those there, but we're going to distribute through, so we get minus 5 times 1, so minus 5, minus 5 times negative t is a plus 5t, that's all times I, and then we get a negative 3 times 1, so that gives us a negative 3, negative 3 times negative t is a positive 3t, and that's a j component. So that's that first part. Second part is t times r1, so then we get t times 0i plus 2j. Do it that way, so we distribute. T times 0 is still 0, so that just kind of disappears, and then we get plus 2tj. So we add together the j components, so it's negative 3, and that's going to be our y value, so y equals negative 3 plus 5t, and this is our x component, so x equals negative 5 plus 5t. Okay, so that's where those come from as we parameterize x equals 5t minus 5. Just switch the order, 5t minus 3. Again, could switch the order there. And t is going from 0 to 1, because that's how that's defined. So we do that. Take the derivative of x, so dx would be 5t, dt, right? Take the basically both sides. This is going, dy is going to be equal to 5 dt. Okay, and so then what we're able to do is now set this up. So y squared, that's going to be so y squared is going to be 5t. Oops. 5t minus 3 squared. Dx is 5 dt plus whatever x is, which is 5t minus 5. dy is 5 dt. This is integrating from 0 to 1. And let's see, what can we do? Well, we can factor out of 5 dt, then we would multiply these guys together. We've got this thing squared, is that right? Y squared. Let's see, this is yeah, sorry here, I'm getting different answers than they're getting, but so we square this out, so 5t minus 5 squared. We're going to factor out a 5 dt, so I'm going to put the 5 out in front, 0 to 1, the dt on the back. We're going to get this plus this. Oh, I see. Oh, now I see, because when I wrote it on the paper I wrote it wrong. Now I got, okay, we got the right answer. Okay, so when we FOIL this out, we get 25 t squared. 5 times 5. We'll get 5 times 3 is 15. We get 2 of those, so we'll get a negative 30t. And then we get negative 3 times negative 3, which gives us a positive 9. From this part, we're going to get a plus 5t minus 5. Okay. And so when we combine like terms, this 5 stays out there. We go from 0 to 1. We get 25t squared. Negative 30 plus 5 gives us a negative 25t. And then we get a 9 minus 5, which is 4. We gotcha. dt. We integrate piece by piece. So you just leave the 5 out at the very end. This is going to be 25t to the third over 3 minus 25t squared over 2 plus 4t. That integrates from 0 to 1. When you plug in 0, these all become 0. Times 5 is still 0. So then we plug in 1, and we should get 5 times 25 over 3. Plug in 1 minus, plug in 1, 25 over 2 plus 4. Common denominator 6. This will be 50 over 6 minus, this is 375 over 6. And I guess you could do the same thing with the 4. 6, it's going to be 24 over 6. We'll add that all together. So 6, let's see, 50 plus 24 is going to be 74 minus 75. So it looks like a negative 1/6 times 5. It looks like we get negative 5/6. So let's see what they came up with in their great wisdom. They did negative 5/6. So this is what was throwing me. And I think the problem is, now I see why it throws me. They have 5t minus 3. Their error was right here. X, when you put in x, it's 5t minus 5. So they made an error here, but then they got it corrected down here. So that's, and then this should be a square. It's not times 2. So it's really, I don't know. We pay so much for these textbooks and stuff, they should find these kind of errors. But I make them myself, so who am I to complain, right? Anyway, there we go. An example using the parameterized version. Okay, let's keep moving forward. And so the nice thing is, I guess, you can fast forward as need be. So the second one is it's a little bit easier. We'll kind of just walk through here. Since we can put x in terms of y, it's following along the parabola. We could just say x is 4 minus y squared, and then y is just equal to y. We don't have to bring in any extra stuff. And there we're just going from the curve. And let's go back. So we're going along this curve, which is x equals 4y squared. And so we can think in terms of y, we're going from -3 up to 2. Okay, -3 to 2, and y is our variable. So we go through this. So -3 to 2. We integrate, and we have the same starting place, y squared dx plus x dy. We use this substitution, sort of, x is 4y squared, so dx is going to be 2y dy, and so we make those substitutions. Dx is -2y, come back here, dy, y squared stays y squared, x we replace with 4 minus y squared, so we did that, dy, and now we've just got one dy, so we're actually able to integrate just nicely, combining the terms as they should be. So this is -2y to the third minus y squared plus 4. Integrate each piece, going from -3 to 2 gives us the answer 40 and 5/6. Now, usually we do not like to see mixed numbers because it looks like multiplication, so I don't know why they did that. Anyway, so in general, we can parameterize over a value of t, and one of the things we can see, it gives us an orientation of the curve. That t is generally chosen in a way that it's a parameter that's increasing, and so we go from A to B in an increasing way. Now, if you were to go from B to A, so in the reverse direction, that's going in, the parameter is now negative. Notice it really is the same thing, but gives us a negative this way, so that would switch the boundaries, and so we come up with a nice little rule that helps us out. If we're going in one direction but we want to go to the other, we can do that by changing the sign on the boundaries, changing the direction of the boundaries, and that introduces a negative in front, or the other way around. Yeah, so either in terms of x or in terms of y, changing the direction changes the sign of the answer. So x and y change signs as we reverse the orientation, but when we're talking of the curve itself, they don't change directions because the change in s is always positive. Line integrals in space, so this we get into 3 dimensions, and we're just going to expand it out. We parameterize x and y as we've done before, but we let z be equal to z. So this is kind of like, what do we do, the cylindrical coordinates. We could parameterize sort of, what do we say, polar coordinates here, and then z just equals z. And then we do that. So what we end up with when we're in space is kind of what we did in 2 dimensions, but now we've got the third. We've got x, y, and z. We've got this square root, and remember, this gives us sort of the length of the curve, and then we multiply that by the function, and that's what gives us our area. So a lot, very similar to what we've done before with 2 dimensions, but now we've got 3 dimensions. Okay. And again, just saying that this integration occurs as long as the sums occur, and as long as we can, the limit as the number of little segments goes to infinity, we end up with that. And then we get 10, so we could do dx, dy, dz. And again, these are not triple integrals in the sense, but they are added together, and there's different integration going here. So we can do these type of problems where we have dx, dy, dz as long as we have a single parameter t. Okay, so that's kind of the trick, and it's nothing too different than what we've been doing, but now we've got three variables to contend with. Let's take a look at this one as an example. So we want to evaluate this integral of y sine of z ds, where c is a circular helix given by the equations, and so we know we're going to integrate from 0 to 2 pi. That's what t is going to do. These are our equations, so what we're going to do is go ahead and substitute. So we'll get the integration. Y is going to be sine t. That's that substitution. Sine of z is, well, that's just sine of z. ds, remember that's going to be the square root dx dt squared plus dy dt squared plus dz dt squared dt. We'll let t go from 0 to 2 pi. So let's get this integration, this part inside here. What's dx dt? Well, dx would be minus sine t dt, right? So and we're going to square this, so that'll become positive. dy is sine t, so y is sine t, so when we take the derivative, we're going to get that y is cosine t, making that get squared because of this. And then dz is just dt, so it's 1. There's our dt on the back side. So we get sine squared plus cosine squared, which is 1, right? Sine squared plus cosine squared is 1 plus 1. So we got square root of 2 dt. Wait, what did I want to put here? Oh, well, that's sine of z becomes sine of t, right? We've got to get all down to one variable. So this becomes sine squared. Okay, 0 to 2 pi, not just 2. That's simplified fairly nicely, and I'm going to just kind of keep moving on. How do we integrate sine squared? We do a substitution. So we'll walk through this. We get our sine squared, cosine squared, plus 1. What they've done is, okay, inside here is the square root of 2, right? Sine squared plus cosine squared is 1. 1 plus 1 is 2, so they move that to the front. They use the identity that sine squared is 1 minus cosine of 2t. So that's the standard one, or actually 1/2, 1 minus cosine of 2t. When we integrate that, that integrates into t minus 1/2 sine of 2t. Where's this t come from? Go through, you got 1/2. That's t to 1. Oh, then they put that out front here. So they bring this out here. Okay, I got it. So they bring the 1/2 out. That's there. 1 integrates to t. Cosine of 2t integrates it to sine of 2t, but using the chain rule, you've got to divide by 2. Gotcha. 0 to 2 pi. You can plug those in when you plug in 0 for t. Sine of 0 is 0, sine of t is, so this all 0 on the back end. At 2 pi, sine of 2 pi, that's actually 4 pi, that's also 0. So this is 2 pi, the 2's cancel, so you get square root of 2 pi. Okay, so again, we just use this, this formula for being able to integrate and parameterize. Okay. We're getting there, almost. Fundamental theorem of calculus just gives us that, remember when we integrate, we're thinking of this as an antiderivative, or this is a derivative of something, so we get the antiderivative, and we go over the limits from b minus the limit to a, so that this is really the sum of this Riemann sum thing, right? As long as it's continuous. So that's just stating that that's the fundamental theorem of calculus, and that's what we've been using all along. And how are we going to use that when we use it with line integrals? Okay. So a gradient vector of f is 2 or 3 variables is sort of is a derivative, right? It's a partial derivative. And so if we integrate that, we get back to a particular function, and we can take that over its limits, which might be a function in itself. But then that's, so when we integrate a gradient, we're getting back to a function. So if we could figure out what that function is, that makes that integration that much easier. Okay. So here's an example that we were given. The gravitational field is this function, and notice this is a bold x. So this is really, this x stands for x, y, and z, so it's three-dimensional. We've got this times x over x, absolute value to the third, so that's really going to be like an x squared, where some particle has a mass little m, and we're going from a point 3412 to the point 220 along some smooth curve. So we're going to talk a little bit more about this, but it's a conservative vector field, and in fact this function is equal to the gradient. So the original function that it comes from is this one, and we see this square root of x squared, y squared, z squared, and we think back to those derivatives that we had earlier with the square root. That's where the connection is. And so all we're going to say is that to integrate this function is to integrate the gradient, and that means we just jump back to that original function we had, which is down here. So we're just plugging in the values into this. So we get the function value at 220. You plug those in, and you get this one. You're plugging in 3, 4, 12. You plug those in, you get that, and then when you sort of factor out and combine like terms, this is the value we get. So just kind of wanted to point out that when we're integrating a gradient, we go back to the function it came from. Okay. Independence of a path, and again, this is going to be a lot of theory. We're going to get a test that will allow us to tell us whether something is independent and whether it's conservative, and we're going to use that. Okay, so a lot of this is just building on theory. So in general, if we go down two different paths, the integrals are not going to be equal, because again, these are two different boundaries, right? However, if they're two piecewise curves and they have the same initial point A and B, if we're talking about the gradient, then they are equal. If C1 and C2, they're different paths, but they start and end at the same place, as long as the gradient itself is continuous. So what that tells us is that the line integral is a conservative vector field and really only depends on the initial and terminal points. We're going to see that we've got some things, we'll find some ways to be able to prove whether the vector, it's really a conservative vector field or not. Okay, so in general, We could go along this closed curve, this little loop in a particular direction, right? Um, and it's independent of the path. It doesn't matter where we start and end, what the path it is, um, as long as we have the same initial point and the same terminal points, they're going to be equal. So we call this a conservative vector field, and that the paths it's independent of path. We call the path closed if it's looks like this. So if its terminal point coincides with the initial point. So if the starting point is the end point as well, then it's a closed path that looks like this. Okay. And again, we could have A going to B or B going to A. So as long as the 2 points are the same, we're in good shape. Okay. So C goes from C1 to C2, so we go all the way around by doing that. Notice C2, if we went in the opposite direction, this is from earlier, so if we went from A back to B, then that's going to be a negative, right? So going in the opposite direction here. However, C1 and C2 have the same initial and terminal points, so that means that they have to be the same. So that means that this integration equals 0 whenever we have a closed path. So this will, when we have an independent, when independence of paths and they're closed, the integration will always be equal to 0. So we can take any of the 2 paths going from A to B, and we take one path going forward, one path going backwards. As long as we go from A to B, go all the way around the path, we end up with 0. Okay. So again, this is just kind of getting us to a place that, okay, that happens, which that means that when we integrate C1, we're going to get the same thing as when we integrate over the path 2, those two different components or halves of the path, right, around the loop, that these are going to be the same because they've going from the same points. And we get this theorem that this integration of this vector field is an independent of path only if the integration equals 0. If and only if it's equal to 0. So it works both ways. So if it's equal to 0, we know it's independent. If it's independent, the integration will be equal to 0. Okay, so that's a theorem that's proved. We're going to use that to get a little bit further, and we're going to talk about the domain being open and things being connected. So let's take a look at a few pictures. So if F is a vector field and a continuous on an open connected region D, so open and connected, then this integration is independent of the path in D. F is conservative vector field on D. That is, there exists a function such that the gradient of F is equal to the vector field. Okay. So how do we determine whether or not F is conservative? We could determine whether or not it's independent of path simply by, if it was equal to 0, then that was a proof. But how can we show it's conservative? Well, let's say we've got this vector field is some function pi plus qi. If it's conservative, then p and q both are continuous first order partial derivatives. So we get this function which is equal to the gradient, right? The partial of x, p would be the partial of x, and q would be the partial of y. And then we can take it a little bit further. Going on to the second partials would be equal, remember. Therefore, we can show that if this function is conservative, this vector field, if it is conservative, then the first partials, partial of p with respect to y and the partial of q with respect to x, will be equal. However, we cannot prove the converse if they're conservative, that this will happen, except if the regions are of a special type. And what kind of type do they have to be? They have to be simple, and they have to be closed. So for a simple closed curve, and simple means that they do not cross themselves. So this is not simple because the path crosses itself. Simple if they do not cross themselves. Closed if the beginning and the end are the same. So kind of the idea of what closure is. Additionally, the region needs to be connected, so there can't be holes within the region. So there's nothing that we're taking out of the domain. They're not two separate regions that are separated. It's a closed region, simple connected region. So that's kind of what we need. If that's the case, then we've got Theorem 6. It tells us that the partial of p with respect to y and the partial of q with respect to x will be equal. So that's sort of a way of proving that the vector field would be conservative. If we know that it's conservative, these have to be equal. If these are equal, it has to be conservative. If these are not equal, then it's not conservative. Okay, so let's take a look at two examples, and we'll actually be done for the evening. Okay, determine whether or not the given vector field is conservative. So what we do here is we call this P, we call this Q. And remember, we're going to take the partial, I think that's the right symbol, with respect to y. It's always the opposite one. And we're going to take the partial of Q with respect to x, and we want to see if those two are equal. The partial of P with respect to y, derivative of x, since it's a constant, would be 0. Derivative of y is going to be -1. Right, that's it. Q, we're taking the derivative of q with respect to x, so x is our derivative, so that's 1. The derivative of -2 is it's a constant, so it's 0. So this one is equal to 1. -1 does not equal +1. These are not equal. This is not conservative. Okay, that's really all there is to it. So you figure it out. You find the partials. First partial is -1. Second partial is 1. They are not equal. Therefore, it's not conservative. Okay. Example B. We're given a different function and asked the same question. I forgot to animate this part, but yes, we could see that the domain is going to be everything. There's nothing to take out of this domain, right? So the domain is all real numbers. So again, we set, I forget where I've got everything. This is P, this is Q. So we're taking P with respect to Y, so that's 0. This becomes 2x. So the partial of P with respect to Y is equal to 2x. And when we do the partial of Q with respect to x, so that's going to be 2x. That's 0. Hey, they look like they're equal to me, yeah? So we can say these are conservative because they're equal. Okay, and that's pretty much all we have to say. They're both equal to 2x. And it's an open domain, a closed interval, or the loop. It's so yes, it fits the there's no holes in there, so we could say the vector field is conservative. Whew. And now we're done. I'll get to work on next week's videos. I'll get those posted by Sunday night. Thank you all. And I hope you're all doing well, staying safe, staying healthy. Take care. Bye.